When's our exam?
Monday.
Friday, right? No, Monday, okay. Monday in lab, what I'll do is, again, just like I've done in the past, I'll start the class on Monday, meaning this time. I'll open it up to questions. I will answer questions as long as there are questions. When the questions stop, I go into a new material. Okay, the same format. Where's the material start? Definition of voltage difference. Where does it end? Basically with the stuff we're going to be doing today. Okay. And must be set in the back. Okay, so I want to do a couple more things here. So we had a dielectric the other day. What was a dielectric? Anything that goes between the plates of a capacitor. So let's do an example of this here. Okay, so let's say I have a capacitor here. This is D. This has cross-section area A. And I'm going to put a metal slab here. And let's say that it has some thickness, let's call it L. So this right here is L. I want you to find the new capacitance here. Find the new C value. Yeah, this is going to be some charge out of plus Q. This is which on it minus Q. Okay. You tell me how to find C. And when you take the exam on Monday during lab, you most likely have to find C for something. But whenever you find C, it's just a definition question. Okay, what is the fundamental definition of C? Always, always, always.
Epsilon naught.
No. Q over the voltage difference between the plates. So again, your definition of C is it's Q over V, and this right here is your voltage. Which is this absolute value of the delta V here with this. So what do you have to do when you calculate a C value? You have to calculate these individual values. Okay, meaning it's almost always this one here you have to calculate. Hey, how do you calculate a delta V? Integral. It's negative integral. There's some initial function. E dot dl. Okay. So we have to do that in this case here. Okay. You tell me how to do this. I'll give you a hint. Very important that this is a metal. You know anything special about metals? There's no E field here, right? So the E field, the inside of metal. So you take your little path here like this. Here's your little DL vector. Now let's go the other way. Here's your little DL vector like this. And here's your electric field. I can make that bigger because it's going to kind of crunch it up. Yep. Plus plate, negative plate, E field like this. And just out of curiosity, tell me physically what's happening while there's no electric field inside this metal. What did he say? This right here is our dielectric. Anything you stick between the plates of a capacitor is a dielectric. You put peanut butter there. No, but if you put peanut butter there, it would be a dielectric. Okay, why is that gonna just tell me in terms of words why we'd have no electric field there?
Comes on top of them.
Okay, the field going this way is going to actually induce some negative charges on the top. We're going to get positive charges down here. And how's the electric field go for these? And again, these are called induced surface charges. How does the electric field go for those induced surface charges? Yeah, they're going to go this way here. Right? And the electric field from these plates are going like this. Okay. What do these two fields do in between here? Yeah, in this case, they're going to perfectly cancel. And they perfectly cancel. You end up with this. It's you. This is D. This is L. And here's the path. So the little DL vector is going to be like this. Okay, this, I shouldn't use L here since this is an L here. Maybe, okay, is that going to be okay if we use the same thing here? You want me to call it something? I can call it T. Then we get it changed. Well, I'll leave it like L. I should call it T. Okay. So here's our L, or E vector goes like this. Okay, you tell me now what's going to happen with that integral from our initial stop to the final stop. What's special about the electric field for a parallel plate capacitor? It's a constant. Okay, so E for parallel plates. Constant. When I do this, you get the following. It's just on this minus integral E dl. Cosine is 0. Cosine of 0 is 1. And what's going to happen here? It's going to come out, but then you have to be a little careful here, because when you do this, what are you going to do? You're going to integrate from here to here, then integrate from then here to here, then integrate from here to here. Okay. So if you pull that out, that's fine, but what is in the integral of that dl vector going to be? So you're going to get D. Correct. What will you get?
D minus L.
You're going to get D minus L, because you're going to integrate from here to here. So that'd be the E times this distance. Plus the electric field here times this, but the electric field here is 0, so nothing here. Then you're going to get then the electric field times in this distance here. So this whole thing here goes to this minus E. D minus L. Because there's no electric field in that region. So what happens here when you put this in for your C is this Q over your V. And you're going to pick the absolute value of it. So I get this Q over E, D minus L. Now what do we do for this E? What do we say is E for parallel plates? What is it? Sigma. We'll grab some up. You put that in here. Hey, how do we define sigma? Over area. The Q's go out. Why is it really good that the Q's go out? Because in the end, what does C never depend upon? Or V. And so you're only left with geometric factors for your capacitor. So these come up, and so this is me C equals epsilon naught A D minus epsilon D minus L. So that's what would happen if you had a metal dielectric there. Okay. Now I want to figure out how much energy is stored in a parallel plate capacitor, and then get the energy density, because a lot of you are going to probably end up taking, at some point, you probably end up taking the optics course. Or if you're doing any type of electrical engineering, you're going to need to know this. I want to show you the energy stored in the electric field. Okay, any questions with this? Okay. Let's ask, what is the energy? Stored in let's say a capacitor. Okay, so you need one thing, recall. No, I should just, let's move on. Let's ask, what is the power given across any electrical element? Now, we haven't done a lot with power. Okay, I don't know how you define power. We mentioned it before, but we haven't done a lot with it. It's going to be kind of the work or the energy expended per unit time, or the work expended per unit time. There are variations on it. So your power P, okay, it's going to be your change in the energy unit time, or sometimes you'll see it like this: the change in the work unit time. There's depending on the situation here, you have different. So let's get the units for these. Okay, so what do you measure energy in? Students in second semester physics. That's making me cry. Thank you. Okay, joules. Time is going to be seconds. We define a joule per second to be a watt. Okay, just a W. That's a watt. And what I want to convince you is that for any electrical element, let's say this is any electrical element. Okay, if I have a current I going through here, let's say this is, let's say I have to put a voltmeter here. And the voltmeter is measuring V. Your power is always going to be I times V. Doesn't matter what it is, it'll always be I times. And I want to prove that. True. So this is true for resistor, this is true for capacitor, later on an inductor, a diode, doesn't matter what it is. So let's say we have this. I have a voltmeter here. This voltmeter is measuring V. And this, when you measure a voltage, what is that really? That is really a change in voltage. Okay. So this is really a change. Well, how do we define change in voltage? And let's say maybe we have an exam on this on, let's say Monday, perhaps during lab. From 320 to 510, just, just make it specific. Delta V is,
Negative integral, I have, you got.
and we beat on that, go one step more back, I should say. We got that from using the original definition of the change in the electric potential over how much charge you're moving. Okay, so we called it this delta V here. You're changing the electric potential energy over Q. So your change in the electric potential energy is going to be Q times delta. Oh, I could even write this properly. This should be a U. Okay. So what I'm going to have here is I'm going to have a little charge here. I'm going to say here's my little charge. I'm going to call that. I'll call that DQ, and that DQ is being moved across here like this. So what am I saying is the voltage difference across here? I'm calling it V. So this is going to become V. I'm still on this. Okay. How much charge am I moving? DQ. So this is DQ. I'm saying that's going to have some change in energy dU. I'll call this my DQ here. So I have that. Okay, let's divide both sides by dt. And does that have a name?
I.
That's I. This is my buddy. This is going to be my power. This is a change in energy between time. So the power dissipated or supplied by any electrical element is always on a speed. Okay. So now let's apply that to a capacitor. Let's look at a circuit here. This is V. Here's my capacitor like this. I'm going to shut my circuit, and I'm going to start charging this up. So what I want to do is apply P equals IV to a capacitor. Okay, so I have P equals I. What's the voltage across capacitor? Voltage across capacitor is always, right? Right, your Q equals, I think the Q equation is always easier. CV. Okay, so this is really Q equals CV. We're looking at how it varies with time. So V is always, for a capacitor, Q over C. Hey, what's my definition of I? dQ dt. I can write this power here. I can write the power as the energy, the change in energy per unit of time. I'll call this the power. It's going to be the U dt. This is Q C dQ dt. The dt's cancel, and this gives me this. Okay, so if I want the total energy stored in that capacitor, what do you do? Yeah, you're going to integrate this. You're going to integrate this from when it has no charge, let's say, no charge being stored. This is a maximum charge. Well, there's no charge being stored, there's no energy. It's fully charged, and it's the full energy U. So this gives me U. And this gives me what? This will give me Q squared over 2C. That make sense? What's another way to write this? What do I know about capital Q? Is there another way to write that? CV. Or I can write this as U equals CV squared. QC. One of the C's go out, and this gives me 1/2 C V squared. Here, right here, they're both the same. Okay. So if you double the voltage across the capacitor, you actually then double the energy stored. Okay. Now I want to calculate where the energy is. Again, for those of you who will be taking optics at some point, this will become really important. Even if you're not doing optics, it's going to become important. Okay. So the energy stored in the capacitor is actually stored in the electric field. So I want to be able to write this in terms of the electric field. So let's write U equals 1/2 CV squared in terms of the electric field. E. Thank you, people are pros of this. Okay. So U equals 1/2. How can I write C for a parallel plate capacitor? Epsilon naught A over C. Let's see. Okay, now, what is the voltage across the parallel plate capacitor? Well, it's the electric field times. Remember, if you do that delta V equation, integrate this line here, the electric field is constant, you get the E times in that separation distance D. This ends up becoming this ED. There's actually a minus sign there, but it comes in square. So what does this give me? This gives me 1/2 epsilon naught A over D, E squared, D squared. Or I can write this as 1/2 epsilon naught E squared A times T. Okay, I'm going to draw a little picture here. D, and it says cross section area A. Geometrically, what is A times D? This is the volume. Volume between the parallel plates. If I take that over here, and you get this U over AD, this is your energy density. There's going to be 1/2 epsilon naught E squared. Boom. So this is your energy density. associated with an E field. So if you triple the electric field, what are you doing to the energy density? You're increasing it by a factor of 9. That'll become important because, again, if you end up taking the optics course, you're going to look at light. Light's going to have an electric field component, and the energy in that electric field is in that wave is going to be directly related to that electric field squared. Okay. Questions? Make sense? Okay. One more thing. One last point. Okay. What is the power dissipated by a resistor? Okay, what did we say is the power across any electrical element?
E equals IV.
P equals IV. So for anything you have, you can say that the power across the resistor is going to be the current going through the resistor. We'll just say I times your voltage across the resistor. Hey, what do you know about the voltage across the resistor? That's IR. So you get our famous I squared R. So if you want the power dissipated across the resistor, it's always I squared R. Okay, we use that actually quite a bit. Okay. Make sense? Let's take an example of this. Okay, I don't know if I should show you this again. Okay. You get a new car stereo. What's the important thing about it? It has to be loud because you want everyone to know you have a new car stereo. So what do you have to do? Independent of the temperature, you roll down the windows of your car and you drive around campus blaring your music. So everyone can see you have a new car stereo. Okay. How do you guarantee that you actually have the maximum output going to your new stereo? What do you have to do? Or let's say you're just in your dorm room and you have to make sure that everyone on your floor knows that you have a new stereo. Okay. So again, you have to blur this. What do you have to do? Well, how do you get the maximum? How do you guarantee it? I want maximum power dissipation in my speaker. You do something actually a little bit different, right? You do what's called impedance matching. Okay. And so I want to show you exactly what it means to be impedance matching. So what happens here? So let's say here's your power supply. And here's your stereo. Here's your speaker. Okay. I need a model for this. Okay. So what would be a model for this? How can I model my power supply? I'll put little dotted lines here. So here's my little model. I could model it as a battery, right? So this is going to be the V here. That's fixed. I can't change that. Well, what else would the power supply have? some sort of internal resistance. So this right here, I'll call this R, the power supply. This is internal resistance. Well, how can I then model that speaker? You can say it's nothing but a resistor. We'll bring this over here. Call this RS. Okay. And what I want to do is we want maximum power dissipation. Across the speaker. Why? Because it's important for everyone to know that we have a new speaker. I cannot live in a dorm anymore. I did it in my youth. I could not do that anymore. I just no. It's beyond me. Somebody took away my PhD and said I had to do it all again. Turns out I do not have that stamina to do that again. Okay. The condition is going to be that if you want maximum power dissipation, I want the internal resistance of my power supply to match, to be equal to the resistance of the speaker. And that we're going to find out later on is that we're going to look at resistance more generally, and it's going to be called something called an impedance. And I'll explain why it's called an impedance, not resistance, later on. This is actually an example of what's called an impedance matching, where I want basically the resistance of this to equal the resistance of this, and that guarantees I'm going to show you that those are maximum power here. Okay. So we will see. We will show. For maximum power dissipation. Resistance of the power supply has to equal the resistance of the speaker. And this is called impedance matching. So if you look at like the power supply or the speaker itself, depending on how the system is, you have different places where you can actually change the internal resistance on these things. And then it's entirely for this to maximize the power output. Okay. So let's just go through and set this up simply. If I were to say, what is the current going through this circuit right now? What would you do? So here's your proof. What is I through the circuit? Okay, you have an exam coming up on Monday. This is about an easy question you'll get, which means you won't get it. Okay. So what would be the current going through here? C equals from this right here.
The over R.
What's the R? What?
RPS plus RS.
Perfect. Okay. What do you know about these two resistors? They're in series. So the whole circuit really reduces to this. I have V, and I have this R equivalent, which is my buddy R the power supply plus R the speaker. So if I want the current going through here, it's going to have to be V of R equivalent, or the current is going to have to equal V of R of the speaker, or I should say the power supply plus R of the speaker. Okay. Well, what has to be the power dissipated by the speaker? which is also the same as now, I squared R. So this is going to be I squared R the speaker. Okay. So what this is going to give me, this is going to give me V over R power supply, it's RS squared, and it's RS. Okay, you people who are in Calc 3 or in differential equations or something beyond Calc 1. If I want to know the maximum power supplied by this, what would I do? You're engineers and physics majors and math majors. You're more than capable of answering this question for me. Okay. If I want the maximum power dissipated, what would you do? You're going to take the derivative and. Okay, let's start with the derivative. What will you do with the derivative? You people who are in Calc 3 in differential equations. And set it to 0. So we can take the derivative, and you take the derivative with respect to R sub s. Okay. And I'm going to then set that equal to 0. And then I'm going to solve for the R sub s value. So what we're going to do. There. Okay. Does this have a name? I'm going to rewrite this in a little slightly different fashion. I'm going to write this as V squared RPS RS to the minus 2. If I take the derivative of this, does this have a name? What? More. What would you do to take the derivative of this? Okay. Tell me why you're not going to use integration by parts when you're taking a derivative. Okay. You're all making me want to just basically, I can feel my little heart starting to tighten up. The blood is flowing through less and less of my body now. Okay. I'm starting to pass out now. I'm going to have to call 911. Say we killed our physics professor by not being able to explain what to do with this. Okay. Okay, what happens if I have this term here being multiplied by this term here? I might want to use. Yes, you use a product rule on this. So you get V squared, that's a constant. Okay. What's the derivative of this? How do you take the derivative of that? Okay, you pull down the minus 2. Comes this guy here. Negative third. This comes along to the right. And you just have to write RPS plus 1 from R, yes, RS, and minus 2 because the derivative is 1. And you set that to 0. Okay, the V squared is a constant. I can divide through by this. I'll take this to the other side. And so this gives me RPS. The 2 here. Plus RS minus 3 RS equals RPS plus RS the minus 2. What do I do? I'll clean it up. How do I clean that up?
RPS and RS, like some of the cancel.
Okay, how many?
And -2. So you're left with 1 over RPS.
So left with 2 RS. I take this to the other term by multiplying by the thing cubed. Okay, that will give me what?
Yes, RS.
RPS. RS. Take the RS to the side here. So if they both have the same resistance, they have maximum power output. And that's called impedance matching. So the speakers often have little places where you can change the internal resistance. You're basically matching it to go to with the power supply. Okay. Questions? Okay, let's do one more thing. And then we start, okay, then tomorrow we start magnetic fields. And magnetic fields are going to be one big example of a cross product. You're going to have to have cross products again, go over them. And we're going to have like 8,000 different right-hand rules, and they're all going to merge in your head. So you have to be a little careful with them. But we're going to have this right-hand rule and this one. And they're just have right-hand rules that don't stop. Okay, one more example. And we're going to follow it. Okay. So this is going to be, has some charge here, Q. This is maximum. C, this is R. At t equals 0, I throw the switch. The switch is thrown. And the capacitor discharges through the resistor. I want to calculate the total amount of energy dissipated by that resistor. Okay. You tell me entirely how to do it. R across, good. It's going to be I squared R. And why am I using a lowercase I?
Varies.
Because I is going to vary. Hey, do we know anything about I? What is I always? dq dt. Do I know anything about Q for a discharging RC circuit? Perhaps you even used it in lab yesterday. Recall. For discharging. RC circuit. Q is what? Use an RC in it. Okay, so it's Q. Total charge E.
-2 RC.
T over RC. Hey, so what's my current? Let's see Q dt. Hey, what's that equal? There's a Q.
Over RC to the -R.
RC here. Okay, so remember what happens with the exponential. The exponential just comes along to the right. So you always get that, but then what goes in front? What goes in front, it's a derivative of this with respect to t. So the derivative of this with respect to t is minus 1 over r. So you get that. Okay? And that comes in squared here. So my power dissipated by the resistor is R times minus Q over RC, e to the minus T over RC, quantity squared. If I work this out, that gives me Q squared over RC squared, because we have an R squared here, cancels one of the others here. E to the minus what? Yeah, if I square that exponential, I get 2t over RC. Okay. And you tell me to figure out how to calculate the energy dissipated in that resistor. I mean, so across that resistor. What is power in terms of words? Well, it'd be the work per unit time or the energy per unit time, right? This P here is du dr. Yeah, I'm sorry, du dt. This guy here. We're gonna take over the dt and then integrate both sides. We're going to integrate from 0 to, if I want all the energy dissipated, how long do I have to wait? Time. How long do I have to wait? I want all the energy dissipated. Infinity. Okay, let's see what we get from that. Okay, so I'm going to get U. I'll pull out the Q squared. I'll pull out the R and the C squared. You tell me what the integral of e to the minus 2t over RC is. Nope. You get the exponential back here. It's going to be evaluated at 0 to infinity.
RC over negative 2.
Yeah, so it's going to be this minus RC over Q. So what does that give me? This gives me Q squared minus over 2C evaluated here. Okay. What is this? So I put in the upper limit, I get what is e to the minus infinity? Okay, it's a decaying exponential. What is e to the 0? 1. So this gives me this minus Q squared over 2C, 0 minus 1. I get Q squared over 2C, and that's your energy dissipated. Why does it have to be that? Why does that make perfect sense? How much energy did we say is stored in here? One half Q squared over C. That's your initial energy stored here. This is your initial energy stored. Where does the energy go? The energy is all dissipated by the resistor. So it's just nothing but conservation of energy. All the energy stored. It's dissipated by the resistor. Okay. And there ends half the class. Okay. That ends the electricity part. Now we basically repeat absolutely everything for magnetic fields. And the nice thing when you get to magnetic fields, a lot of everyday devices we get, that's actually we need magnetic fields for those. Okay, have a good day. So the exam stops here.